Welcome to Big Boy Physics. Today our topic is based on Maxwell Boltzmann distribution, that is from kinetic theory of gases. Well, if you are wondering that today we are going to do some kind of proof that why such kind of big v square into e to the power minus mv square by 2kbt terms comes while we write dp by dv, then you are correct. Today we are gonna actually derive it. Okay, so let's get started. Before that, you need to know some important concepts about probability. Suppose A is a event, another event is B, and these two are independent events. Okay, then probability that A and B both occurs is given as probability of A into probability of B. This is first concept you need to know about. Second concept you need to know is that probability that a particle, if you have a large number of particles, then the probability that a particle has energy between E to E plus dE, that is dPe, is given as proportional to e to the power minus m e to the minus e by kbt into dE, or you can write it as equals to c times some this expression, exponential expression, but c is the normalization constant. Hope you get it. So let's begin with our journey of deriving the Maxwell-Boltzmann equation. First thing, we'll be explaining that there are three modes of motion for a monoatomic gas. For monoatomic gas, that is along x-axis, y-axis, or z-axis. There are three modes. Then can you tell me what is the probability that it will have velocity is equals between vx to vx plus dvx? For a particle, if you want to find a particle in the bulk that it has velocity from vx to v plus dvx, then we can write kinetic energy required will be equal to mvx square by 2kbt, where kb is the Boltzmann constant. So what I'm gonna say that probability dp v as a function of vx can be written as e to the c into e to the minus mvx square by 2kbt into dvx. Now observe that Vx, Vy, Vz all are independent and all are mutually equally likely, because all each of them are independent, and observe that each of the directions are equally likely. That is why in case of if we write PVy, in that case also the normalization constant actually remains same. It will be c into the power minus m vy square by 2kbt into dvy. Similarly, dpvz is equals to c into e to the power minus mvz square by 2kbt into dvz. Hope you get it. Now, can you tell me the probability that it will have velocity between vx to v plus dvx, vy to v plus dvy, and vz to v plus dvz will be c cube e to the power minus mvx square plus vy square plus vz square by 2kbt into dvx, dvy, dvz. Now, if you observe the Maxwell-Boltzmann equation, it will be written in this form that f of b, small f of b, is given as, or df of b or dp, whatever you want, by dv is written as 4 pi m by 2 pi kt whole to the power 3 by 2 into v square e to the minus mv square by kbt. Now, in this case, what we consider is the absolute velocity. We consider v square to be vx square plus vy square plus vz square. Okay. Now, what we'll consider now is the case of v vector space. In this v vector space, there are three mutually orthogonal coordinate system. Basically, three mutually perpendicular axes x, y, and z. Now, we are considering a small volume dvx, dvy, dvz, and we are trying to find a probability that a particle stays within this region. Now, vx, vy, vz are all mutually equal. Now, in this case, I will be considering dvx, dvy, dvz as some infinitesimally small volume d tau. Okay, d tau, and vx square plus vy square plus vz square is basically representing this vector v. Now, considering A small thin spherical cell which is of volume having thickness dV, then we can say d tau is equals to 4 pi v 4 pi v square dV. So basically this will give me the radial distribution of velocity, means radial distribution of probability of particle having velocity between v2 v plus dv. Okay, hope you get it. Now just we need to substitute d tau as dv 4 pi v square dv. You will get um, d tau is equals to c cube into 4 pi v square e to the power minus mv square by kbt, 2 kbt dv. We know that integral dp 0 to infinity will come out to be 1. It is called the normalization, right? So integral dp 0 to infinity will come out to be 1. So I can say 4 pi c cube integral v square e to the power minus mv square by 2k bt is equals to d into dv is equals to 1. Now to solve this integral, we need to use integration by parts. How? Now observe one thing, that I will be writing this m by 2k bt is equal to some constant alpha. So I can write it in form integral 0 to infinity v into e to the power minus alpha v square. We know you can solve this integration by substitution. Okay. And another integration you need to know to solve this is integral 0 to infinity e to the power minus x square dx is given as root pi by 2. And if we put minus alpha x square, then it will be 1 by 2 root pi by alpha. So this will be my final result. Evaluating this integration, you will get something like mm, 1 by 2 alpha. First we'll be using parts, that is v into e to the power minus alpha v square by 2 alpha, negative sign, 0 to infinity plus e to the power minus alpha v square by 2 alpha integral 0 to infinity dv. Final result you will get 1 by 2 alpha root pi by alpha. Another 2 factor will be there, so it will be 1 by 4 alpha root pi by alpha into 4 pi c cube is equals to 1. So I can say that cancelling these 4s, I'll get c is equals to alpha by pi under root, where alpha is equals to m by 2 kt. Substituting it, you will get m by 2 pi kb d, right? So final result comes out to be f of v is equals to 4 pi c cube into this big expression. So it will be f of v is given as 4 pi m by 2 pi kt whole to the power 3 by 2 v square e to the power minus mv square by 2 kbt. Okay. Now what will be dp? That is the probability is dp is equals to this big expression into dv. Now, so I basically derive the Maxwell-Boltzmann distribution equation. Hope you get it, get all the understanding all those. Now, can you tell me what will be the number of particles having such amount of velocity, that is between v and v2 dvx, if the total number of particles are n naught, which is much greater than, which is, or you can assume the order to be of na. We generally apply Maxwell-Boltzmann distribution, all those statistical laws, in case of large number of particles. We cannot apply for one or two particles basically. Okay, you must remember it. So n naught is generally of order approximately to n naught, na by, or you can say na by 10 to the power 10, whatever you want. But it will be a very large number. Okay, so hope you get it. Now you can find average velocity, average RMS velocity, then most probable velocity. Well, most probable you must have already differentiated this equation, this f of v. You must have differentiated and found the maximum of this function and found the maximum probable velocity. Well, generally the most probable velocity is derived in most of the institutes also in 10 plus 2 level. But deriving this average v and RMS velocity, this involves a little bit of calculation and Gaussian integral. Only one thing you need to know is integral e to the power minus alpha v square 0 to infinity is given as 1 by 2 root pi by alpha. This is a very important theorem you must know to solve the Maxwell-Boltzmann equations. So problem of this session, let's take it. For a gas following Maxwell-Boltzmann equation, that is f of v is equals to 4 pi m by 2 pi kt whole to the power 3 by 2 v square e to the power minus mv square by 2 kbt dv. We can say that average v, that is this quantity represents the average value of this quantity x. Okay, then we say average value of v into average value of inverse velocity is given as some constant a by pi. Now my question is, find a. Look at this question carefully. Whenever they will ask in any JE or Olympiad, they will either try to make you derive the equation, the above equation, or they will give you this direct formula, or they will just give you this constant c and ask you and give you the variables in terms of b square, all those, and tell you to find some other expression. Okay, you don't need to worry about remembering or memorizing this equation. Well, I have tried to derive it, so hope it makes you to easily memorize it. And another thing to say is that you can also answer this question in the comment section. I will post the answer a bit later in the comment section itself. Okay, and I am also posting another handout of Murad Basirov. I have taken it from Fizoli. You can go through it once, because they haven't used the above concept, that is the probability of particle having energy. What I have used here, yeah, this one, they haven't taken exactly this one. They have tried to solve a differential equation. I'd like you to go through it and learn something new. Hope you enjoyed today's video. Thank you and have a nice day.